Okay guys, in this video I'm gonna show you guys how you could model a composite beam in ANSYS Workbench. Alright, so ANSYS has a module for pre-processing laminates, so it's called ACP. You can insert it to your workplace by double clicking on that, and then you come here and I'm gonna make add a composite material to my library. I'm gonna use there are like some preset material in ANSYS. Let's say I'm using epoxy e-glass unidirectional, and the properties of that material, you see the main mechanical properties you're going to need to model the material are listed here. Modulus of elasticity in X direction or longitudinal, and then transverse T and T prime must be the same. Poisson ratio, this is new LT, this is new LT prime, and then this one YZ is actually TT prime. This is the largest because in that direction matrix is gonna do this property is going to be affected mainly by Poisson ratio of the matrix. Shear modulus, you see you have two of them equal, and then one of them TT prime is different. Okay, it's smaller because again in TT prime direction it's mostly affected by the matrix. Alright, the other ones properties are not needed to do a stress analysis. If you want to do failure analysis, you're gonna need these. So these are not needed. So these are for your project, or if you are interested in defining a new material, you need to calculate these and insert them here. So I'm using that class epoxy as my material. Then next step in modeling is you go to the geometry. You can import your geometry from like other software, or you use it here. You use that ANSYS itself, space claim, or modeler, geometry modeler to do that. And let me open it. So we have to wait until it opens. I want to model a simple beam. Alright, so we wait and we wait. Okay, so it opens. Now I'm gonna model it using okay, I wanna model a beam. So let's say it's like 25 millimeter as the width. The length is 100. Okay, so this is a surface now. I close this and I go to model. We have to define thickness for the surface, but as I said, the final thickness is going to be determined by the number of plies you put, and each ply is going to have its own thickness. So you can the final thickness is going to be controlled by that. But in order to mesh, we need to define a thickness. So I am starting. Okay, so I open the model and let's see. Okay, so I'm waiting for this guy to open. so you come here for thickness. I'm gonna say my thickness is 1 millimeter, and I need to mesh this. This mesh is gonna be used later for analysis, so it's better to have it like refined a little bit. So you can add refinement here. You guys know how to do that. So you go here, select all. What happens when you say select all? All of them must be selected. Yeah. Okay. So if I say select all, you have only actually one face here. Okay, so and then I can refine the mesh. Alright, that's now good enough. So this is the mesh, but next I'm gonna add plies to this model. So you can update the project. You should see the check mark here. Yeah, that's interesting. It's very slow. Workbench might come. Alright. Okay, I see check mark on model. So I go here now. On setup, I'm gonna set up the layup here. So I'm gonna do this 2 times. Once with like a symmetric layup, and and show you guys that when it is symmetric, you're not gonna see coupling between stretching and bending, but when we do unsymmetric, then we're gonna see that coupling. So we have epoxy here effective. I'm gonna define a fabric. So something be careful is this, the unit, standard unit is a meter, but I'm gonna change it to millimeter, and fabric is gonna be, you can have different types of composite lamina here defined, but if you want to have like a hybrid laminate, but if you don't, you have just one type of lamina, and then you define it here. And okay, so element set is like in a model that I made. Let me show you. Yeah, this is our model. Let me connect my mouse. Then it's gonna work better, so hold on. Yeah, looks like my mouse is out of battery, out of charge. Okay, so let me use my other mouse, which is not wireless. Alright, so with mouse, this is our material, right, our model. So I have elements here, and all elements, you can define like element sets, and then for each element set you can define like what material you can assign a certain material, a composite material to those elements. But right now I'm gonna assume that this material is like homogeneous, and everywhere I'm gonna have same material, okay, same E-glass epoxy. So all elements are gonna be the same. Next thing is rosette. So the rosette are used, they are like material coordinate systems, and by defining new rosette you can define this is like gonna be like a local coordinate system you can define here, and then based on that you can define the direction of your fiber. For this one I'm gonna assume that it's gonna agree with my global coordinate system. As you see here, you see this green one, it agrees with my global one. This is the default, but if you want you can change it or define a new one. Okay, you can just right click and create rosette anywhere you want. So and then orientation, select set. So once you have the rosette, you can define, based on that rosette, orientation of the fiber. So this is, you see, this is my primary direction. So with respect to that arrow, that axis, you can define your orientation of the fiber. So element set, I'm looking at those elements. And then the orientation, you know what, I'm gonna say what arrow you see there, I'm gonna consider that as my direction for fiber. And then my reference rosette is gonna be this one, right? The rosette we were talking about, like by default came with the model. All right, so now I am ready to define my layouts. Okay, so modeling groups, you go here, you say I'm going to create a modeling group, I'm going to call it this, and then this modeling group 1 is going to have, let's say it's going to have 3 plies. Alright, so let's say it's going to have 3 plies. So orientation set, I'm going to use this one. For ply material, let's say everything is fabric 1. Ply angle, at first I'm going to do it symmetric, and then I'm going to change it. Okay, so 61 is like one layer, and then I'm going to do another one. So the second one, again same thing. And ply material, as I said, you could have it like a hybrid layout, but right now I'm using all same lamina, but what is happening is they are with different orientation. Okay, so this one and fabric 1, and then this one again 60. Alright, you know what, let's just start with like not symmetric one, and then I will make it symmetric after that. Alright, so we made our layout, so now let's update the model. Alright, so we can look at each layer, the orientation of the fiber. So let me see which one is the fiber direction. You see, this is the first layout, first ply. Second layout is 0. Second ply is 0. The last one is -60. So let's look at the first one and the second one again. So alright, then I need to make a solid model here. So I create a solid model. I'm gonna, my element set is all element set, and then there's nothing else I need to determine here. So define here. So I go like this, and then I say update the model. Okay, we have made the model, so now let's close it and update the project. Alright, so now I'm gonna put a static structural here, and I take the setup here to model, and then we're gonna transfer the solid model, and then I'm gonna open this guy to apply loads. Remember, now it's like not symmetric, 60, 0 and negative 60. So let's see what happens. Okay, so here is my jihad. You know, we have like 3 layers as you see, and we have the mesh, everything. So I'm gonna add a fix support to this end. You know, let me rotate it. Actually, apply to this end. And then other side, I'm gonna apply, you know, a force or a pressure. You know, I'm gonna apply pressure, but the pressure is gonna be is like, I don't wanna apply pressure. I wanna like pull it. So I apply like 100 megapascal. The unit was Pascal, so let's say 1 megapascal. 4, 5, 6. Alright, so now let's solve it. Okay, so now let's look at the formation. So as I said, I expect to see bending. You know, you see this? What's happening? I am actually, I have not only that, I have twisting too. You know, it's like bending and twisting. Right? Look at the layers. Let's look at the layers. One layer, top layer is 60. Middle layer is 0, and then I have the bottom layer negative 60. Now you guys see how it works. You see the deformation. Now next, what I'm gonna do, I'm gonna look at the other case when you have you know, symmetric plies. So then see what happens. What I'm gonna do is I'm gonna go here, right click, and go and change one of the layups. I'm sorry, one of the plies. Okay, so you come here, modeling group, this bottom one. Look at this one. I'm gonna change that to 60, and let's so that last layer we changed it. If you want to see like fiber orientation, you can see that, make sure that it makes sense. You know, this first layer is like 60, the other one 0, and this one should match now the you know, the top layer, which it does. You see that? Is it? Yeah, they're the same. Alright, so now that we have updated everything, I'm gonna go out and update the model. So now with this update we have to go to model again and take a look at, you know, readjust the boundary condition. Alright, double click on the model. I want to go there and take a look at the boundary condition, see how it has changed. Alright, so you see the fixed support, I need to reapply it again. So let's say I'm applying it to this guy, to this face, and then I'm rotating it here. The pressure, I'm gonna apply it to this face, right, and this is it. So we run it. This time is symmetric, so I expect to see no bending. Right, so let's look at plies. I want to make sure that the plies are 60, 0, and 60. Let's look at the deformation. Look what is happening. Now it's awesome, right? Yeah, so this is what I'm expecting to see. Now let me continue with the stresses. For example, if you want to look at the stresses, normal stress in X direction in one of the plies, right? So you can come here, select the ply. I'm sorry. You go here, click on here, and then select the ply you're interested in. And then you say apply. And then here you can select this top bottom is the average, and in the top layer, bottom layer, and then middle of the ply. So that makes sense. How much is the stress in X direction there? So you guys can select which one you're interested, and then you say evaluate. It's gonna show me the stresses right in X direction. This is not, by the way, longitudinal or transverse, right? So what is important for us is longitudinal and transverse. So for that you can come here. Where was it? Oh yeah, I'm sorry. This is like fiber coordinate system, so that's a good thing because you have here global coordinate system of fiber. So fiber is more meaningful because when you say X direction for fiber, it means longitudinal direction. So stress in longitudinal direction, the maximum is what is 0.5, 0.7 megapascal. But if you go global, it's actually in X direction in your global coordinate. That's not something useful for us, right? So we are interested in, if you want to study failure, we are interested in longitudinal sigma L and sigma T, right? And we want to make sure that the ply is safe by those failure theories. So look at this. So I'm going to change this actually to fiber coordinate system, which is more meaningful for me. And you see what is the max is. So the top ply is having just 0.7 megapascal. So let's say I wanna go with look at the middle ply. I wanna look at the middle ply, and the middle ply. Okay, I'm sorry. I click here and then go here and then middle ply, apply, and then say I wanna look at the midpoint. And fiber coordinate system. Let's see what stress that one is going to experience. You see, this is far larger, right? It's like 2.6 megapascal, the mid layer. And then if you look at the bottom layer is bottom layer is let's see how much it's gonna experience that guy. Yeah, you see it's symmetric, right? So top layer and bottom layer, the maximum stresses are the same, and the middle one is experiencing larger. And this makes sense to me. You know why? Because you remember top layer was 60, the middle one was 0 along x, and then the bottom one was again 60. And you see that my stress was along x-axis, and mid layer has fibers in that direction, so that's why it's taking more load. So these three layers are actually sharing the force, right? They're each one is contributing, each layer, to hold that pressure that I apply to the face. But the middle one, which has the stress fibers along x-axis, is going to take larger load. Larger stresses. So this makes sense, right? All right. So this is how you guys can look at like post-process the results. And again, let's take a look at the deformation. And this is like for the bottom layer. So if you look at the total deformation, again, because of symmetry, this is what I'm observing, right? It's just a stretching due to that load at the end. But if you don't have symmetry, which was for the first one, let me go back again. Yeah, that's a good idea to show you guys again how to change it. So you come here, modeling group, this one, if I change it to -60, it's gonna be unsymmetric, right? -60. So now I have 60, 0, and -60. So how does this guy work? I'm closing it, and then I update the project. Yeah, I have to go again to model and reset those boundary conditions. Alright, we'll go back. Alright, I come here, fix support. So alright, and then this pressure thing applied to this face. Alright, and now let's run it again. I want to show you the difference. So now I have 60, 0, -60. The deformation first. You guys see that we are pulling it, but a lot is happening. We are having like twisting. You have combination of effects. So, right? And then the stresses, let's look at the stresses. The top layer and fiber longitudinal sigma L is what? Which design is better, by the way, the first one or this one? This one, highest sigma L I have is 1 megapascal on top layer. Mid layer is 2.5. And the bottom is 1. So, looking at these stresses, comparing with the previous layup, you guys can see which layup was better in terms of stress. in terms of like deformation wise, this is not something that's like pleasant, right? If you're designing that beam to carry the stretching, that pressure or that pulling force, then obviously we don't want to see twisting. Twisting is not a something you want to see, right? So this is how you guys can model beam. So you know, you can I'm going to share this model with you. You can play with it and see, you know, if you like, you can apply different forces and see how it works. Alright, so I'm gonna save this right now with current setup and email it to you guys.